cover them over the course of his presentation. So I'd just like to welcome everyone to this AST presentation. I have a slight promotion, which you can probably see up on the screen, which is that the Association for Software Testing, we have an annual conference called CAST. The CAST for 2020 is coming up in August, plenty of time away. It's happening in Austin, Texas. And right now we've got early bird sales of tickets, which means that we've got really good deals on tickets. We've got tutorials by Angie Jones, Lisa Crispin, and a number of other people for CAST. So if you are interested, just go to the associationforsoftwaretesting.org and take a look. So I would like to now just switch over and say today our guest for this webinar is Yarin Podoler. He's presenting on machine learning, Codeless, Selenium, and sort of how those tools are important and coming up, going to be a big deal in the testing space. Yarin is a co-founder of TestCraft. He's also the chief product officer. He's going to give some more details on his background. So Yarin, let me flip it over to you.
Hi, everyone. Can you hear me? Give me thumbs up if you can hear me. Okay, can you hear me well?
I can hear you just fine.
Okay, perfect.
Yep, cool.
Okay, so I'll start by, I'll share my screen and let me see that you can see it, okay? Can you give me thumbs up if you can see the presentation?
Great.
Okay, perfect. Thank you. Okay. Okay, so hello, welcome everybody. Good morning, good afternoon, good evening, and good night. My name is Yarin, as mentioned, and I'm going to talk about machine learning and Codeless Selenium. And a bit technicalities before I start. Just let me take this off. A bit technicalities before I start. Okay, so this presentation I usually do in about 50 minutes. I'll try to squeeze it into 40 minutes, so I might talk a bit faster than usual. So please ask question on the chat. I have an iPad over here, so I might be able to see it, hopefully. And actually, I prefer that you would ask questions and not leave them to the end, so it would be more interactive talk. I'll hope that I can get to them. I hope. Okay. So let's see if I forgot something. No. Okay. So a bit background about myself. My name is Yarin. I'm 34 years of age. It happened 3 weeks ago. I'm happily married +2. You can see Eli Nido on the right side over here. I started coding since I was 13 years of age, so about 20+ years of experience in coding. Today, I am one of the co-founders of TestCraft, which is a Codeless Selenium test automation platform. And I really love sports and particularly cycling. Okay, so this a very short background about me. This is my email, yarin@testcraft.io. Feel free to approach me with any questions. After the webinar, I'll be happy to answer every question that you have in person. Okay, this is my plan for today's webinar. We're going to talk about machine learning and Codeless Selenium, and we are going to start with a basic overview about machine learning, very basic overview. Then we're going to switch and focus in the testing world, in the QA world. We are going to discuss a practical testing problem about how we solve it today, how most of us solve it today. And then on the third part, I'm going to suggest some kind of a machine learning-based solution for that particular problem. And on the fourth section over here, we are going to analyze the result, which personally, I think this is the most important part, and we'll get to it later on. By the way, I see that my iPad and chat is not working, so I'm currently turning it off. So if you have any important question, please interrupt me in the middle if you think it's important. Hopefully, we'll get to the Q&A at the end, and we'll have time for it. Okay, so this is the plan for today. So dive in really quickly into overview about machine learning and what is machine learning. So I'll start with the definition. And the definition is quite nostalgic from 1959 by Arthur Samuel, which personally I love the most. And he said that machine learning is a field of study that gives computers the ability to learn without being explicitly programmed. So it seems quite straightforward, but it's a bit tricky. And I'll show why, or identify a cat in a picture. We would like to have some kind of a picture. You see over here on the left side, we can see a cat. And the algorithm that we are going to write is going to identify whether or not this one is a cat. So the pretty straightforward way to do that is by writing some code that does it. We are having some features of a cat. For example, we know that every cat has 2 ears and have 2 eyes and have some fur and has a mustache and is cute. And if we combine all of those features together, criterion together, then we can positively say that this image contains a cat. Okay, so this is pretty basic example of not a machine learning. Okay, so this is not a machine learning because we explicitly programmed or explicitly mentioned of the feature and told the computer how to identify this cat. So this is not a machine learning algorithm, but don't get confused. This is an AI. Okay, so a bit confusing. AI, artificial intelligence, and ML, machine learning. So machine learning is subcategory of AI. This kind of algorithm called an expert systems, they are AI, but they are not machine learning. And I'll show you some problem in such algorithms. For example, on the left side, you can see 2 images of a cat. I think most of you would agree with me that those are cats, but those both images fall for at least one of those criteria. For example, this cropped image at the top, we cannot determine the numbers of ears, so it will fall on this criteria. And the bottom one doesn't have a lot of fur, so you might say that this is not a cat, or actually the algorithm will say that this is not a cat. Okay, so those both are examples of false negative. The algorithm will identify those images not to have a cat in them, but it will be wrong. On the other hand, on the right side, you can see a tiger in the cat family, but it's a tiger, and all the criterion are true for this kind of animal. Okay, so this would be a false positive. The algorithm will identify a cat, but it should have been identified as a tiger or not a cat. So this is a false positive. So those are the kind of problems that we have in expert system in the case of the expert not being actual expert. Okay, so this is an AI, not a machine learning. So let's try to suggest a different approach to the same task, to the same goal. And what we would like to build is actually some kind of a black box machine learning algorithm, which have an input of an image, the same image that we saw over here, the cat image. And it outputs a yes or a no. It is a cat or it is not a cat. Okay, so this is, if you heard about it, it's a simple classification problem to classify an image to 2 buckets, cat and not a cat. But this is what we would like to achieve. So actually, in order to build such algorithm, there are 2 phases. The first phase is designing the architecture of the algorithm. I won't touch on that. But the second part, which is, I think it's more trivial these days, is the training phase. And how we train a machine learning algorithm. Basically, we provide a lot of images, and their required output. We call them labels. For example, on the left side, you can see 4 images of a cat with the labels yes. So we are telling the algorithm or training the algorithm that those images are cats. And on the right side, we provide different images with the label no, and we are training this algorithm and telling him that those images are not cats. Okay, hopefully, by somehow tweaking internally, you'll be able to identify cats from non-cats images. Okay, so this is the training phase. So very basically speaking, there are two types of machine learning algorithm. There is the supervised learning algorithm, which is basically what we did over here. We provided the supervised learning, we provided the image and the output, the yes, no in this particular case, and we provided the data to the algorithm, and we trained it according to the data we provided. So it was supervised by someone. Okay, so this is supervised learning. The other type is unsupervised learning. Actually, there's a third one, reinforcement learning, which I won't touch on this, but just let's go over the unsupervised learning to give you some kind of understanding of the second major type. So unsupervised learning, very different from the supervised learning. We give him some kind of data, and we don't know, or the algorithm actually doesn't know about the data or how the structure of it. And the one thing that it does, it actually clusterizes the data into different groups. It depends on the features he finds in the data. So in this particular example, we gave him some kind of shapes, and the algorithm can provide us with two clusters. This is an example of two clusters of the big images or the big shapes and the smaller shapes. Now, pay attention that the algorithm doesn't know that those are big and those are small. It just knows that those are in the same groups and the three other ones are on a different group. Okay? It doesn't know anything about our data. It just can identify similar patterns in data and cluster them in different kind of groups. Okay, so this is the unsupervised learning. Okay, any questions up until now? Let's see if I can see the chat. So this is a very basic overview. Anyone with questions?
Doesn't look like it now.
No, okay. But by the way, feel free to ask whenever you want. Okay. So let's talk about a practical problem. And I'll show you some kind of a Selenium demo. Okay. So let's say that I would like to write an end-to-end test, some kind of a scenario. And let's propose a simple scenario. Let's say that we would like to go into Google, okay? Enter hello world. So this is the most basic scenario that I could think of. Clicking on the Google search, navigating into images, okay, clicking on the first image, and validating the see more link over here. Okay, so it's pretty straightforward. I already prepared the script, so let's go over it really quick. Okay, now let me just increase the font a bit so you can actually see something. Okay, should be much clearer now. Hope it's better. No. Okay, hope that you can see it, but actually what we have over here is first, this is a protractor script on top of Selenium. You can see the configuration file. We are going to run this JavaScript file with Chrome browser, and we're doing some stuff at the beginning. It's irrelevant, and this is the actual test. So the actual test consists of a few steps. The first one is navigating to Google, to the page that you would like to go. Second thing would be to identify the text box element, and we are identifying the element by a name locator with the value of Q. You know what, I'll try to increase the font. Just a second. Let's do this 15. And do this 122. it should be better now. Okay, so we identify the text box element by the name with the value Q. So the locator is the name locator, and we are going to send some data to the text field, hello world. Then we are going to identify the search button by a CSS locator with the value Google search. We are going to wait for it and clicking on the element. Then again, we are going to click on the images, identify the images, and then click on it, identify the first image, click on it, and then I verify that the text see more is there. Okay, let me run it really quickly so you can see that it actually works. Hopefully it will work. Okay, you don't see the screen, so. Okay, so this is the script. I'm going to click on the first image and validate the see more. So everything worked as expected. Okay, so quite straightforward. It took me about 20 minutes to write the test, and not too fast, but okay. Now let's change something and see what is the problem. Okay, so instead of hello world, I want to just send TestCraft. Okay, so I'm changing the data that I'm using inside of the test. Let me just run it again. Sorry, the computer is really slow today. So we search for TestCraft. The data is changed. The scenario stayed the same. Okay, and it failed. Okay, and you can see that it failed because we could not identify an element with the data ID locator. So it's really weird if you think about it at first. We only changed the data, and something broke. Okay, and why it happened? It happened because sometimes something, might be the data, might be some kind of a developer changing something, causes the test to break with no specific reason, because we just could not identify the element. Now, you might say that, okay, but I don't change the applications so much, so the probability of it failing is not that large, and I don't need to worry about it. So we went out and checked it. Okay, so we did a bit of testing on our side. We took a sample of about 100,000 test steps from our own customers, and we were amazed to see the results. From those 100,000, from one test to the other, there were about 45% change. So if we run the first test and then we run the same test a day later or a version later, there is a 45% for something to change, even if we didn't change the code. Okay, might be some kind of attribute change, the data was a bit differently, the network was acted a bit differently. So 45%. And on the bottom table, you can see a bit of what happened. For example, let's take the position. Okay, so the position, or position of an element, it appeared 100% of the time for all elements. Okay, all elements has position on the page, but 21% of them changed from one test to the other. Okay, so 1 out of 5 was changing their position. Elements changing their position from one test to another. It might be due to running tests on different resolutions, responsiveness, or other things. Another attribute, let's take the ID. ID is considered to be very resilient. As you can see, it appears only less than 40% of the time, 39% of the time, which means actually we cannot rely on such attribute to appear in our tests. But the amazing thing is that it changes 15% of those 40. So if the ID appears in your application, 1 out of 6 that it might change, okay, in probability speaking. Okay, so this is a bit of data of what changes over time. Let's talk a bit about probabilities and why it's so important. Okay, so let's say that you have a group of Selenium coders in your organization, and let's say that you have a good developers team, and by good I means that they can actually select the most robust attribute when they write their Selenium test. Okay, so they can identify which attribute would change less, so they can write more resilient tests. So when I say good, it means that 9 out of 10 times they would select the most robust attribute, which means 1 out of 10 times they would choose a much more fragile attribute. If you take 1 out of 10 and multiply it by 45% probability of breakage, you will get about 4.5% breakage rate. Okay, so this is when you have a good team. On the other hand, if you had a not so much of a good team, they will probably nail 5 out of 10 times, which means if we multiply it by 45%, we will get to 22.5% probability of breakage. So as you can see, there's a huge variability between 4.5%. This is 1 out of 20 tests break. This means that 1 out of 4 or 5 tests break. So a large variability between those. So this is a very crucial problem, okay? And you need to take care of it very early in the process if you have a Selenium developers. On the other hand, let's say that you chose to use some kind of codeless Selenium solution or any other kind of codeless solution. So it's obvious that you need, because the codeless solution doesn't know your application, it doesn't know how to choose the attribute smartly, it needs some kind of a brain in order to get to those 4.5. If it won't have those components of a brain or a machine learning which adapts to your application, we will get to those probabilities, to the 22.5 probability very fast and even higher. So instead of a codeless Selenium solution, you will have eventually a useless solution. You can write tests very easily, but they will be very fragile. Okay, so this is the problem, and this is why it's so problematic, especially with codeless solutions. Okay, any questions up until now? Anyone?
Yeah, I don't see any in the questions channel. So if anybody has them, please just go ahead and put them out, and we'll go ahead and get them addressed.
Okay. How is the speed so far? Everything is okay? Understood? Okay, I'll keep going, but if you need me to slow down a bit, just mention it or ask questions, feel free, okay?
Great.
So I'm going to the third part, the machine learning-based solution. So let's discuss a possible solution, let's try to design it, and let's see if it has potential of working. Okay. When we think about a machine learning algorithm, if you remember from like 7 minutes ago, it needs some kind of an input. In the case of the cat, it needed an image. So it needs some kind of data for it to work with. Okay, so let's see. Let's say that we would like to identify the Google search button as we did in the very simple scenario earlier on. So what data can we extract from such element? So I'm sure you all know, if we are going to Chrome or any other browser that you like, we right-click on it, we are inspecting the element, and we see some kind of DOM tree. Okay, I see that we have questions. We have questions? Since when was a tiger not a cat? Yeah, you're right. It's not as good example as I thought it would be, but yeah, but it's a tiger. Okay.
There's another. Yeah. There's another question about why not to use specific test specific attributes.
Okay, so that's a good question. I would like to address it now. If you use a specific attribute as I shown before, they might change. If you are going and synthesize your own attributes inside of the test for each and every element, it will be very resilient, and I strongly suggest doing so. But sometimes, and maybe a lot of the times that we see and we experience, such approach cannot be taken. For example, let's say that you would like to automate some kind of CRM or a Salesforce application or any kind of external application, or maybe the quality assurance team are not talking very well with the developers, and the developers do not want to add attributes to their code. So you need to rely on what you have, okay? And this is most of the case, and most of the times you don't know if what you have are strong enough. Okay, hope that I answered the question. If not, please feel free to ask again. Okay, so going back to the machine learning algorithm solution that we're trying to suggest. So we are trying to extract some data about this element, and we are inspecting the element in the console, and we can see this DOM. So all of these are attributes of the element, and as a QA, I can probably guess which attribute will be more resilient. For example, the Google search value would probably be very resilient down the line. I can locate it using that. But if you think about different languages, it won't apply. Maybe the ARIA label, the same with the languages. So every attribute I can find a scenario that it will not work. But those are the things that we can play with. But is it so? Let's think about a bit differently. Instead of just taking one attribute of the Google search and identify it using a single locator, why not taking all of them? And why not taking all of the attributes, not only on the Google search button, but on all of the elements? So let's extract all of the data that we can capture on all of the elements, attributes such as the idea, the placeholder, the ARIA label, the appearance, the position, and others. We have a lot more, and have them organized in such a matrix like so. As you can see, we have the rows are the elements. We have image, text box, search button, feeling lucky button, language link, and all others. And on the columns, you can see the attributes of such elements. For example, the image is 275 by 200 pixels. The name is not defined in the image, but on the text box, it's defined as Q. The position of the search button is 42% on 41. So we can extract all the data real time on this particular page on all of the elements and have these large matrix fed the machine learning algorithm. So this would be one aspect of the data. Now, in order to build such algorithm, we need some kind of base element to be able to identify it. So when we want to identify the element, we give the algorithm both the large matrix that we just provided and the original base element that we found like 5 versions ago. Okay, so those would be the inputs of the machine learning algorithm that we would like to build. The data on the current web application and the data of the original element from 5 versions ago. Okay, it will mix up in the machine learning algorithm, and it will provide eventually an element from the table with the highest probability, and this is important, highest probability of being the correct element, up to a certain point, of course. I'll show you an example. Okay, not an example, but I'll show you a design of such an algorithm, a very overview, a very basic design of such algorithm, and then we'll go step by step, and we'll try to understand the concept, the different thinking of what we are aiming for. So if we'll dive into the machine learning algorithm, this is the design. So these are the building blocks of the algorithm. None of those are actually being programmed, but those are the high-level building blocks. So we have the 2 inputs. And now I'm going to go on a specific scenario just to explain the flow. I will not cover everything, but just the main flow, the data flow. So we have the 2 data. We have the data of all attributes and all elements on the specific time, on a specific page when we would like to identify the element. This is being done for each and every step, for each and every element, this one. other input is the original element that you would like to identify. So if we would like to identify the search button, we are taking the original attributes of the element as it was a month ago, for example, and we are taking them into a scoring mechanism. The scoring mechanism, what it ought to do is just rank all elements based on the score they get with the relevant data, with the original attributes that we already have. For example, if we mix and match all the attributes with the Google image, we'll get about 31%. And I won't get into how we do the calculation, how it's being done, but you get a number. You get 31%. Okay, so this is 31% probability of the Google element to be the Google search button. If you'll see the text and mix and match all the relevant attributes, we'll get about 49% probability. If you'll take the I'm feeling lucky button, which you can see it's much more similar to the Google search button, it will get a higher probability, about 69%. And the Google search gets 94% because it might be that the class attribute was changed, so it's not a fully 100%, it's only 94%. So the scoring algorithm basically categorize or organize all elements with their relevant probabilities based on the original element. Okay? Now, there are actually two scenarios over here. If nothing was changed, we would get 100% over here. Okay, I see that there are a lot of questions. Just let me finish this slide, and I'll address those questions. If it was 100%, nothing was changed, so we could put the original element as it was. Okay? But on this particular case, something was changed. We don't know yet what, but we know that no element has a 100% chance or are fully correlated to be with our original element. So this is the highest probability of being one. So now we are going to the threshold detector attribute. Okay? I'll do a bit of pause. Let me see the questions that we have. Okay, let's see. What do you mean by test-specific attribute like data test ID? Yes, those kind of attributes that you can capture from the DOM itself. It can be data ID, it can be class, it can be style, it can be whatever. Those would be technical attributes. We actually have more attributes that we can gather. For example, how it looks, the color of it. So more of a contextual attributes. So those can be considered as well. Okay.
So I added the questions into the questions panel. So I think the first one of the questions was actually, would you want to add an image of the element in the matrix? Why or why not? And specifically the matrix of element attributes that you had on your slide.
So you can add it. It requires a bit different machine learning algorithm, but you can add it as another parameter. Absolutely, yes. Okay? You can take all attributes that you can think of, or actually you need to be a bit wiser than that, but every attribute that you can think of that you think it matters, and push it into the machine learning. And if you have enough data, that the algorithm would rank those attributes based on their relevancy for this particular element. Okay, so the visual appearance of the element is an absolutely yes. You can use it. Okay.
Great. And then the second question is, and this is, I guess, more just of a general question, but do you have, so the question was like, are we going to get more information about how to implement like an ML-based solution after the session? I would actually broaden this to maybe if you have some recommendations on resources for reading and potentially implementing like your own solution, whether it's through like AWS or I don't know if you want to talk to this a little bit, or if there's maybe resources you would recommend for learning more about like actually how to implement something
how to actually
like
make machine learning.
Yeah.
Yes, actually very, very interesting topic. I won't cover it on talk because this is more of an overview and tackling a particular testing problem, but I'll be happy to share after this talk some great articles that we've been experienced with and some great how-to tutorials that you can actually dive in and test and do it on your own. Okay.
Great, that's fantastic. And then looks like we have one more question, which is when is scoring done in the process? Do you retrain an algorithm every time the tests execute, or after they're done?
Yes, it's not just the test execute, every step of the way. So if we have a test with 20 steps, we have different models for different elements. So actually, we will have 20 concurrent training running at the same time. Okay, so every element is different. We don't build a generic algorithm to fit everything. We actually categorize it based on different elements, but think about it, each element gets its own model. Okay, so we train it. So we train the model or run the model for every step. Okay? So actually, this one runs every step. If we have 20 steps, it will run 20 times on this particular test.
Does that have any kind of impact on performance of any kind?
Yes, a lot of impact. And it's very important to do this very efficiently. This is one aspect. This is more of a technical problem. But we did benchmarks on performance on our end. I'll give you some numbers so you can grasp. For about some pages have more than 20K elements, and we need to identify only one. So, and those are large pages, and it takes us about 100 milliseconds in order to identify elements, in case there are 20,000 elements. In case there are much less, it will take less time, but this is the benchmark that we have as for now. But this is a good concern, the performance, yes.
Great, I think that's it for now.
Okay, great, good questions. Okay, so moving forward with the machine learning algorithm, we've done the scoring mechanism, actually categorize all elements with the relevant score relevant to the base, to the original element. Remember, we are trying to identify this element. Now moving forward to the threshold detector, this component over here, okay, the threshold detector, and it actually eliminates a lot of the elements that are not relevant. Now, I specifically picked a very easy example to eliminate everything, but there are cases that we end up with more than one element. For example, 2, 3, or even 4 elements, and then we use other learning mechanism in order to filter out the relevant elements. But this is the threshold detector. Now, the interesting part. Now, let's say that this was on this particular example, we could identify this element as 94% probable to being the right element. And we are right in this particular case. Now, this element actually moves on to the auto-supervised learning mechanism. It means that somehow the original elements gets changed in some way that we are showing a new algorithm, a new machine learning algorithm. Look, this is the element. It was changed somehow. Here are the new attributes. You have the old element. Here it is. This is the old element with the old attributes. Learn from it. Do something. Be able to understand which are the more important attributes and which are the less important attributes. Okay, so for example, and I'll show you later on, if we can identify that the class was changed on this particular element, we can reduce the importance of the class or improve the other attributes' importance. Okay, and I'll show you later on a real life application how it's not how it's being done, but the result of it. Okay, so this is the actual second machine learning. This is the feedback actually, and then it's being propagated out as the correct element, and the test move forward. And again, the performance issues, this needs to be done very quickly, and you're right. Okay, so this is the basic outline, the basic structure or design of some kind of a machine learning algorithm that you can use in order to identify elements in a Selenium-based end-to-end testing scenario. Okay, let me show you the same example I showed you in a code very quickly, 5 minutes time, to show you how it's being done on a real live application. Okay, so this is TestCraft. I won't go into it, but just explain what we see over here. Let me just rerun the scenario so we'll be able to do the same thing with the Selenium. On the left side, you can see that the test scenario. Currently, I only have a navigate to location. And on the right side, I have a live browser. Okay, so this is live. I can interact with it, and I can add more elements. For example, the scenario was to enter hello world over here and click on the search button over here. Go into images. Clicking on the first image, the hello world image at the upper left side, and validating the get more text, add more link. Okay, so I'm at the breakpoint. I will remove the breakpoint. Okay, so this is the scenario. Okay, so again, I'm navigating, I'm searching, I'm clicking on the Google search, images, first images on the upper left side, and validating the see more on the right side. Okay, so this is my scenario. Okay, fairly easy to create. That's not the problem. The problem is, as I demoed in Selenium, is what happened if you change something. So let's change the data. Let's do the same thing. Let's say we will use it to TestCraft, and let's rerun. And let's see that everything should work. Hopefully it will work. Okay, so we will get another browser, another clean browser, no cookies, Chrome, on the cloud. We are searching for TestCraft now. It's quite quest, but if you were able to see, we are getting different images. This is where it failed in the Selenium script earlier on. Okay. We were able to identify the first upper image left and validate the text. Okay. So over here, actually the algorithm came into place and chose the most relevant element based on the data that it had, and moved forward, and the test completed successfully. Okay, now let me show you what I wanted to show you earlier on. This is the kind of result of the algorithm we spoke earlier on. Okay, so I chose the search, the text box. Over here, you can see a distribution of different attributes. Okay, so those are the attributes that you can see on the Google search text box. What you can see over here, the proportion of each attribute, it's actually the importance of it for this particular element. So as you can see on this particular element, the algorithm was able to identify that the name, which took about 30%, is about 30 times more important than the role. It's 10 times more important than the role and 10 times more important than the size. Okay, so those are actually a weight distribution pie, which show you which attribute is more important. Now, over time, the algorithm will actually change the dynamics of those attributes in order to fit better to the underlying application. And this is the result of the machine learning algorithm. Okay? Perfect. Any questions up until now? We are going to the interesting part.
Doesn't look like it so far.
Okay. Is it really working? That's a good question. And this is the question that you need to ask yourself. And why is that? Okay, I'll show you what we've been doing on those 100,000 test steps that I've shown you before. So this is a nice graph, very nice graph. What it means is actually this is a PMF, a probability mass function. On the x-axis, you can see a probability distribution. It should be from 0 to 100, but the 0 to 60 is not so interesting, so I cropped it. You can see 60%, 65%, all the way up to 100%. And on the y-axis, you can see the appearances, the amount of times each probability appeared in those 100,000 test steps. Okay? What it means? It means that if you go into the 100%, 100% mean I ran the test and nothing changed. Okay? So it's about 57, 56,000 test steps, so on 100%. On the 85%, let's say that there are 17.5, something like that, elements that were on the about 85%. Okay, so this is the PMF of the test that we've shown before. What it means? It means actually that the element on the 100% from one test to another didn't have any kind of change, so this is 52%. The 72.5%, all the way up to 100, it actually means that there were some kind of a change in the underlying application. As we told before, it can be the element change its position. The ID was generated, and that's why it changed. The class was changed because we deployed a new version. Doesn't matter why, but eventually this element didn't get 100% probability. It gets less probability because something was changed. But the green area means that the algorithm was able to auto-correct itself. So this correlates with about 45% of the time. Okay, so this is the green area over here. And we have the possible misclassification rate, which is from about 67.5, actually is a bit to the left, all the way to 72.5%. If we say that the threshold is 70%, that if we're getting closer to the 70, the algorithm might get wrong, actually. As close as we get to the 70, it might get wrong. Over here, we might say that we found, but it's not the element. And over here, we can say that we not found, but the element might be there. And it correlates with 3% of the time. Okay? So this actually what the PMF means. Now, before I talk a bit more about that, I want to get some terminology right. Okay? So there is a thing called the confusion matrix. In every machine learning algorithm, you can find it, you should find it. It's called the confusion matrix, and it's a 2x2 square. And what it means is actually predictive values on the left and actual values on the top. And we'll have positive and a negative, and a positive and a negative. What it means this is the actual value of the element. The question that we are asking ourselves is whether or not the element is in the page. And the actual value could be, yes, it is in the page, or no, it is not, because some kind of an issue. The predicted value is actually what the algorithm predicts it to be. The algorithm predicts it to be in the page or not to be in the page. And there are 4 different sections over here. If the element is in the page, so the actual value is positive, and the predicted value is positive, so the algorithm was able to identify the element, this is called a true positive. Okay, so this is the upper left rectangle. On the other side, if the element was not on the page, we have a negative for the actual value and a negative for the predicted value. So the algorithm was able to identify correctly that the element is not there. So this is a true negative. Okay? The algorithm predicted correctly the negativity of the element to be there. So this is the bottom right side. Now the other ones are actually the more scary ones. Let's say that the element was there, the positive, it was the actual positive side, but it predicted a negative. As you remember, as I explained with the cat example, it was a cat, but the algorithm predicted it not to be a cat. So this is a false negative. The algorithm made a false result, and it is a negative. Okay, it mentions it to be a negative. And on the other side, on the upper right side, the element is not there, a negative value, but the algorithm predicted it to be here. So this is a false positive. So this is very dangerous, actually, the false positives, because it feels like the test moved forward and did what it should have done, but it did it with a wrong element, but we don't know it most of the time until the next 5 or 6 element, and this is very hard to debug. Okay, so all machine learning algorithms are actually a trade-off between false positive, false negative, and the other two. Okay, so this is just terminology. And now we have two different measurements, which are very important. We have the accuracy rate, and we have the opposite, the misclassification rate, which is actually the opposite of one another. So we'll talk about the accuracy. Accuracy is the true positive plus the true negative divided by the total measurements that you had. Okay? And the misclassification would be the other way around, the false negative plus the false positive divided by the total. This will actually show you how much of the time your algorithm get it right. Okay? Those are the numbers for the algorithm that I showed you, or the design that I showed you earlier on. The accuracy of 97.4% and a misclassification rate of 2.6. Now, I think this is very important, not the numbers themselves. If there is one thing that I would like you to take from this webinar, is that you need to know those numbers. Regardless of what tool you would like to use, whether or not you are developing machine learning or your own, or are using different kind of third-party machine learning, it could be a codeless, or even regardless of testing. It is very important to know the accuracy level and the misclassification rate, because this will determine, especially for testing, this will determine whether or not the solution is viable and how much time and effort you are going to invest later on in maintenance. So those are very, very important numbers for you to understand. And if you don't know them, ask them or test them. Okay? Now we have time. I think we have time for Q&A. We have a bit of time.
Yeah, we got a few minutes here. So I've bubbled up a few questions. So I think the top one right now is just how do you detect false positives and false negatives?
Okay, that's a very good question. So false negatives are much easier to detect. Usually they will break your test. So if you are running your test every morning before you're coming to work, or every night, it's irrelevant. Most of the time it will break your test, and then you'll have like, out of those 1,000 tests that you are running, 50 are broke. Now you need to fix those, and you'll have to go into them and find understand why the test didn't move forward and broke. And a lot of the time it will be a false negative. So those are much easier to identify. False positives are much harder, and it will need a bit of much hard digging into the application and seeing what happened previously in the steps before. Now it's, in order to identify those, you need a very good a tool or something that you wrote yourself that can analyze those changes. So it's much harder to do.
Great. So we've got a minute or two left. If anyone else has questions, someone had a question about TestCraft being able to, like, specifically be able to access non-public apps. But it looks like you've got some frequently asked questions around that you guys can do that. But if there are any other specific questions around what
machine
Yarin,
learning, regarding
machine
learning.
learning. Yeah. But feel free to go ahead and post those. Otherwise, we'll just go ahead and wrap up. Looks like we got
Now,
another
again,
question.
feel free, if you have specific questions, you can approach me via my email or via our website, or regarding this presentation or the webinar, machine learning, the solution, or whatever other topic that you'd like to talk about, I'm available.
Yeah, so Scott's asking, so you would need training data for every page you'd want to test and then execute that against every element you'd want to identify? Is that a lengthy process?
Roughly. Eventually, this is true. You'll need a lot of data in order to process each element. But as you go along with the underlying application, you can have a lot of similar elements. So you can actually have correlations between two elements. So you can train one model with the other one's data. So it helps a lot. But that's a good question. A bit more advanced, but a good question.
And then I guess this might be in advance as well, but how would you even know if you have false positives? I think you were saying that with false negatives, you would see failures, right, in your tests.
Mm-hmm.
What about false positives?
False positive, you'll most of the time you'll still see failures, but just farther down the line. So let's say that you have a false positive. Let's say that you have a test with 20 steps, and you have a false positive on the third element. So probably it will fail on the fifth one or on the seventh one. Let's say that you clicked the wrong button, so you'll get to a wrong page, and then you need to enter a text, but there is no text box over there, and then you'll get a false negative on the text. It's actually a true negative, but you won't be able to identify the text ahead because it's not exist, but then you need to debug it and see 3 steps before that you clicked on the wrong element. So it's much harder to debug, but it probably will fail also farther down the line.
And it seems like there's a few questions kind of around this idea of false positives and how to figure out if they're actually like true positives or negatives, or not negatives in that case. So it sounds like this is, as you were sort of alluded to, this is a much more interesting. How do you start to determine this kind of stuff?
Yeah. So everything in machine learning is probabilities. So it's a trade-off. It's a trade-off of what's the margin of true false positives, true negatives, false negatives, and true positives that you would like to actually have. We got a lot of feedback of the margin that you would like to control. There are some systems that you are able to have some kind of levels or margins to accept false positives, and some you don't want to have it all. So it's a trade-off, and you need to know how to play with it depending on your underlying application. But it is a problem.
So let's do one more question. And so the question was, in your experience, are legacy apps harder to use to machine learning on, just like they tend to be harder to automate? Or has that not been the case?
Come again? Which applications?
Legacy applications. So like older there's no example here, but just I would say older applications.
I don't think it's a question of how the legacy or how old they are. It's a question of data. I think there was a question earlier on regarding the attribute. If I would be able to add attributes to each element, it will help a lot. So if you have more data, it probably be much easier with machine learning to do the right thing, or to identify or to achieve your goals or of whatever you're planning. If you don't have a lot of data, for example, let's take an HTML page with a div inside a div inside a div inside a div, and you don't have any other attributes, so it will fail. It will fail on Selenium, it will fail on machine learning, it will fail on any algorithm that you have because you don't have enough data. So the crucial part is the data aspect. You need to have enough data in your application, and if you don't have in your application, then don't go out running searching tools. Fix it in-house. Add more attributes, add more data to them. It will be much more robust.
Great. And so with that, I think this is a good time to end it. So I just want to thank Yarin for doing this presentation. Yarin, Yeah, did you have anything else that you wanted to add?
No, I think
All right.
I've covered everything.
I think so too. All right. Thank you, everyone. And thank you, Yarin. And have a great rest of your day and, in Yarin's case, night.
Thank you.
Thanks, everyone. Bye.